All right, thank you, Ben. So, hi everybody. As Ben just mentioned, I recently graduated from Western Oregon University with my bachelor's degree in chemistry and a minor in biology. Today we're going to be discussing research that I conducted during my senior year alongside Dr. Fair Ho, who is actually presented here before at Open Science. So kind of a second generation, I suppose. We were investigating the green synthesis pathways of copper iodide-based metal organic frameworks, and these are also known as MOFs. I'll refer to them interchangeably within the presentation. So first, you might be asking the question of, well, what is a MOF if you are not familiar with this field? So MOFs are coordinate polymers composed of ligands or linkers around metal cores. So we can see in this image here that you have these metal circles that represent the metal ions and these blue bars that represent the metal linkers, or organic linkers. And when they come together, they make these porous structures that can be 2 or 3-dimensional. And whenever they're 3-dimensional, they actually create cavities, which can be functionalized by adding functional groups to those metals or to the linkers themselves. And you can finely tune the size of the pore by using different sized linkers and the shape of the pore by choosing different metals. So there's a lot of fine tuning that can happen in these structures. To talk a bit more about the functionalization of these porous structures, you can add things like acidic groups, basic groups, metallo-ligands, and you can also just leave open metal sites in the framework, and that allows you to catalyze specific chemical reactions. So to highlight these capabilities, there's actually research being done on the selective absorption of carbon dioxide using these materials, as well as the catalysis of the reduction of carbon dioxide to alcohols using them as well. So they have a lot of possibilities and are very widely applicable. And although those two properties are very interesting, the tunable pores and the functionalization, there's another one which holds great potential, and it's the one that we're really going to focus on in this presentation, and that is the electronic interactions that occur across coordinate bonds, which allow us to tune the electronic properties of these materials by choosing, once again, the metal, the ligand, and the geometry of the compound. To discuss just for one moment about coordinate bonds, though, I think when I started this, when I started this project, I still didn't have a clear understanding of this difference. So here it is. So in an ionic or a covalent bond, each atom is going to donate 1 electron into the bond. In a coordinate bond, 2 electrons are going to be donated from one atom into an empty orbital on the other atom. So here, copper and iodine come in an ionic bond to form copper iodide, but this pyrazine here in the center, a lone pair on either side, and those are going to act as bridges between coppers by donating their electrons into an open d orbital on the copper. So you might be curious how this shakes out whenever you scale it up. Well, this is looking at a different structure. This is looking at HKUST1, which is copper 2+ and 1,3,5 benzene tricarboxylate. This structure is very well researched and has a lot of interesting properties. But if we look at it from just the physical, how this works, you have these benzene rings that are represented here with these black carbons. And off of those benzene rings, we have these carboxy groups, which have oxygens at the end, and those act to link to the copper metal here in blue. And whenever that occurs, whenever that expands in 3 dimensions, we end up with this really unique porous structure where we have a large pore represented by this yellow ball here, and then smaller pores represented by these orange balls. So inside of those, you can catalyze chemical reactions, you can trap gases, you can do all kinds of things. This structure in particular actually has been shown to catalyze the reduction of carbon dioxide, like we were discussing earlier. But this is a copper 2+ MOF, so we're actually going to be discussing copper 1+ MOFs, specifically copper iodide. So to move into the more applicable region, these MOFs were first looked at for their use in crystal engineering because they have this very interesting property where most of these copper iodide-based MOFs have 2-dimensional or 1-dimensional structure. And so the idea is you could expand a larger framework in only 1 or 2 dimensions in order to make more customized structures for crystal engineering purposes. The one that we spent the most time looking into and the most time focusing on, though, are the photoluminescent properties of these materials. So whenever you shine UV light on a lot of these MOFs, they actually produce light in the visible region through fluorescence. So what we see here is 5 light bulbs that have been coated with 5 different functionalized copper iodide-based MOFs, and they're each making a different color when exposed to that light. So this is really awesome. It's a very interesting thing. It's not terribly rare, but they offer a very strong possibility of being used in CFL and LED bulbs in replacement for rare earth metals like yttrium, terbium, and europium. Currently, those are used in very small quantities in order to make white light, but these rare earth metals have environmental and supply issues which make them undesirable for something you want to make a lot of. And so, for a very similar reason, perovskite solar cells also utilize rare earth metals as whole transport materials, or they use these very complex and expensive organic molecules. And so there's some interest in using copper iodide pyrazine systems specifically in perovskite solar cells. So moving into how these interesting structures are made, how they're put together, we have a couple of different options. First, we have our solvent-based methods, which are the most commonly used. So you can have either solvothermal or hydrothermal syntheses, where high heat and high pressure are going to be used with either water or organic solvents in order to make these reactions spontaneous. So in this circumstance, we're going to use a furnace that looks like this, something like this, and a pressure chamber that's going to stop our sample from exploding. So we have this Teflon sleeve here, and we're going to put our solvents and our reactants inside, and then we put that inside of the sleeve, and we tighten that down and put it into the furnace, where it's going to be heated above the boiling point of the solvent in order to increase the pressure inside of that sample. And that's going to make the formation of things that we can't make at ambient pressures and temperatures spontaneous. And so this is really nice if we need to make those structures, but it uses a lot of energy, it requires expensive equipment, and it also requires, in some cases, the use of organic solvents. Solution synthesis is obviously the most common way of making most molecules, but the idea here is you have moderate heat and ambient pressure, and you just put your materials into a solvent like water or organic solvents, and then they can react in the solution phase and then precipitate out in the solid phase. And so with copper iodide, however, water is not an option here. Copper iodide is almost insoluble in anything. The only thing that has some ability and it's moderately soluble is acetonitrile. And so most syntheses up to this point with copper iodide have been done with acetonitrile solution synthesis, because that's what you can get it to solvate in. But acetonitrile has its own health and environmental consequences. So there's a very interesting technique that's come in the last few years known as mechanochemical synthesis, which has been discussed on this channel before. So there's 2 types of mechanochemical syntheses at a very high level. You have dry synthesis, in which you're going to just grind your materials together, literally diffusing them in a pestle and mortar. I wish you could see my camera so that you could see me grinding. But you're going to just grind your materials together, and that is going to diffuse them and allow allow your reactants to come together. The problem with using dry synthesis with no solvent at all is you have a very low diffusion coefficient. Basically, whatever your hand can do or whatever your machine can do, that is your diffusion coefficient. And so this can make the reactions very slow in some cases, and the products are also often amorphous because there's no solvent in order to support the pore formation, which can cause those pores to collapse. So this usually requires the use of specialized equipment like a ball mill. There's a couple of other different techniques that you can use, but the general idea here is you just have these milling balls in the bottom of the chamber, and you're going to push down a piston on top of those at a specified pressure and just continue to rotate around and around and around until the reaction comes to completion. Now we can also use a liquid-assisted grinding in a ball mill. Then the idea would be to use just a small amount of solvent in order to increase the diffusion rate and make the reactions faster. This works well in a pestle and mortar as well, which is one of the benefits of using a liquid-assisted grinding. And so the benefit of this is that you can do it with less expensive techniques, less expensive equipment, and you generally end up with a more crystalline sample because that liquid is still there to support the pore formation. Moving into my favorite one, though, my favorite synthesis pathway that we went through, that we worked with, is accelerated aging. And the idea here is that you just put the materials in close proximity with each other until they react. This is typically performed without solvents, but solvents can be used as additives. And the idea is to mimic geological activity. So accelerated aging is in particular inspired by mineral neogenesis, which occurs when metals are exposed to small organic molecules like oxalic acid in the environment. Oxalic acid is excreted by lichens, and it's also found in guano. And so metal oxalate deposits like this can form minerals such as muolite, which is what we see here. This is copper 2+ and oxalic acid. And other materials like lindbergite and others can also form. In nature, we have a lot of time. Nature has a lot of time to make these reactions happen, though, and we don't have that time in the lab. And so what we do is we add additives, heat, humidity, and microwaving in order to accelerate the aging process. But once you've mixed the ingredients together, then there's nothing else to be done. You don't mess with you don't constantly disturb the sample as you do in a mechanochemical synthesis. You just leave it on the counter and basically let it react. And so the benefit of this is that insoluble metals can be used in these synthesis pathways. For example, copper iodide can be used without using acetonitrile, and metal oxides can also be used. The benefit to metal oxides is that they are earth abundant, easy to derive, and very inexpensive. And so if we can use them in MOF frameworks, then that would be of great benefit to making industrial scale applications more or less expensive. Now, the goal of our research has been to make MOF synthesis more green. So you might ask, well, really, what does that mean? And the idea is to reduce the harm on the environment. And eventually, the hope is to get to the point where we are not harming the environment at all using our synthesis methods. And what this looks like for us is using less solvent. So that way we don't have the environmental impact of solvent releases into the environment, as well as the purification of solvents, which is energy intensive. And just getting away from that entire idea, going more towards solid state reactions, using ambient temperatures and pressures, so that way we aren't producing the carbon dioxide and other greenhouse gases that result from energy production, and using earth abundant materials and metals whenever we can. And so copper is a very earth abundant material, and metal oxides would be even more earth abundant. And going hand in hand with that is to make industrial scale production of MOFs safer and less expensive. To give you an idea of how important that is, currently the MOF which we were looking at earlier, HKUST1, which is one of the only MOFs that you can currently buy from Sigma Aldrich, costs around $24,000 a kilogram. So that makes it very difficult to justify incorporating into industrial processes. And if we can bring those costs down, then it makes these more feasible to go into place of rare earth metals and light bulbs and that kind of thing. So the system which we focus the most on is copper iodide and pyrazine, which just so happens to make a lot of pretty oranges, yellows, and reds. In acetonitrile solution synthesis, we found that no matter what our metal to ligand ratio, we always seem to produce this yellow polymorph that has also been reported very commonly in the literature. So we wanted to see if this would change if we went through a mechanochemical pathway. And so first we tried a water-based mechanochemical synthesis. And we also tried to do a solution-ish synthesis in which we just disturbed the copper iodide into the water while it was reacting. And we got some interesting results. We didn't get very much crystallinity, but we did see much more variation in the color of the compounds produced. And so this made us think maybe something interesting was going on here. And so then we moved on to see if the same thing would happen with acetonitrile, or whether it would be as consistent as the solution synthesis pathway. And what we found is there's a little bit more variability, but generally it was much more consistent than the water-based mechanism. And so we were like, what's happening here? So then during that process, we found something kind of interesting. So I was making a dry mechanochemical synthesis of copper iodide and pyrazine, and I ground them up in my pestle and mortar and poured them into a beaker, which I had just cleaned. Well, I thought that I had dried the beaker, but I had not. And so the bottom was covered in a small amount of water. And whenever the reactants hit that water, they immediately turned a bright orange color, which made me think that I had just ruined the experiment. But nonetheless, we put a cap on the beaker, put it on the shelf, and waited a week. And when we came back, we found that we had made this very dark orange, almost red compound. And when we did an X-ray diffraction on that, which we'll get to, we identified it as being this red polymorph of the copper iodide pyrazine system that had previously been reported by doing acetonitrile solution synthesis of these compounds, and then leaving the yellow product in acetonitrile for over a month. And when they did that, they got a very small conversion over to this red polymorph that you see here. We were able to do this through a much more earth-friendly and a much faster process. And after really working through the ideal setup for this reaction, we came up with this procedure. So the idea is to just dry grind the ingredients, so dry grind copper iodide and pyrazine, and you add water to a beaker, but not to the pestle and mortar where you ground the materials. And then you add those reactants to the beaker and you mix it up into a moist slurry. We seal that beaker up so that way the water can't escape. We heat it up to 50 degrees, and then over the course of about 30 to 40 minutes, the copper iodide and pyrazine will go to this red structure, this red polymorph. Now you see the structure up here. And that's how we derive these bright, brilliant red results. And then, of course, we had to verify our results. And so we first turned to FTIR analysis because that's what we had around in the lab. And we found something, once again, very interesting. So the blue line, this is pyrazine by itself. And down below in red, this is the pyrazine when it's bound to copper iodide. And you see that the peaks seem to be just slightly red shifted in the copper iodide and pyrazine. Well, FTIR shows us the relative strength of the bond. And so that showed us that the strength of the bond was lessened whenever the copper iodide bound to the pyrazine. And this is specifically looking in the fingerprint region. So this is influencing carbon-hydrogen bonding primarily. But we can understand these results by looking at what's called metal to ligand charge transfer. So copper iodide's highest occupied molecular orbital, or HOMO, is a 3d10 orbital. In order to get to the lowest unoccupied molecular orbital, LUMO, you have to add 3.1 electron volts of energy to that electron in order to get it to bump up. And then once it's up there, what goes up must come down, so it jumps back down, releasing those 3.1 electron volts. Well, whenever we see the photon that's released, it's outside iodide, and we see it as white. But what happens whenever you bind copper iodide and pyrazine is that through that coordinate bond, these electrons can now access the LUMO of pyrazine, which is only 2.39 electron volts away. And so the electron can jump up to the LUMO of the pyrazine and then jump back down into the HOMO of the copper iodide and release those 2.39 electron volts as a photon of light. And when we see that, that looks yellow. And so this explains why the color of the compound changes. It also shows us why this weakening of the bonds may happen, because the LUMO of pyrazine is also a pi star orbital. And those of you who have had physical chemistry or organic chemistry may remember that pi star is an antibonding orbital and weakens a bond. And so it results in a weakening of the bonds and a redshift on the FTIR spectrum. Then we wanted to further verify with X-ray diffraction to see if we did in fact get the red polymorph. X-ray diffraction is kind of the standard way to identify these compounds, standard way to see what you made. And It's important to note that on the y-axis, this is unimportant, this is arbitrary, but the x-axis is very important. And the idea here is we blast a sample with X-rays and we measure the angle of deflection that you see whenever those X-rays bounce off. And so this can tell us a lot about the crystalline structure of the product. Well, so in interpreting these, what you're looking for is peaks that overlap. So copper iodide is in red, and the sample is in blue. So we can see here that the sample shares some peaks with copper iodide, but that not all of them. So then there's other peaks that are shared with this red copper iodide and pyrazine polymorph that is from a literature value for this compound. And you can see those peaks overlap, green with blue, and that verifies that we do in fact have what we think we do. In doing research for this presentation and for this paper, we ran across another group who had actually looked at this exact same system and had found that they could make the red and yellow polymorphs by liquid-assisted grinding in a ball mill. And so this group was able to make both of these polymorphs and do so much faster and with less energy and less solvent than the original synthesis pathway. But they were also able to use dry grinding in order to make this orange polymorph that we recognized in our work, but we couldn't find any reports of an orange polymorph in any other papers. So this was actually the first paper to report this orange polymorph, and is the one where, and this allowed us to understand these relationships and what we were seeing. Because then what they noted was that the orange polymorph would spontaneously decay into this red polymorph over here, and that this would happen over the course of about a week, which we saw in some of our samples. And we also noted that, as I said earlier, when you add the water, it immediately goes orange and then decays to red. So this matched our experimental results. They also looked at interconversions between these polymorphs and found that you can actually go between yellow, orange, and red, but what you have to do in order to get from red and orange up to yellow is to add energy. And what that indicates is that that the yellow is a higher potential energy than the orange or the red. And so that indicated something about the thermodynamic relationships between these polymorphs, and we were able to start to track and trace out, the relationships and how these were interconverting from Cappuccino et al.'s work, which was amazing. So we looked at this and we saw, okay, the orange is spontaneously decaying into the red, and the red and the orange both you have to add energy to get up to the yellow. And so that means that the yellow is of the highest energy, orange lower than yellow, and orange is higher than red. And so you can go through that process and start to look at how these are related. They also looked at thermogravimetric analysis, which allowed them to see allowed them to confirm these results. And under thermogravimetric analysis, you basically heat the product until it decomposes, and you can see what the decomposition products are. They showed that the orange and the red both decompose first to the yellow polymorph and then to copper iodide and pyrazine separated. So all of this supported these thermodynamic relationships. However, we were having a really hard time mapping these out, because on a two-dimensional plot, it was difficult. You had to kind of connect the dots with your mind in order to understand how, the copper iodide and pyrazine may become orange and then convert to yellow and then convert to red, all these things. And so we wanted to find a better way to do that. And so what we did was we took a normal potential energy plot, like a standard potential energy plot, and just wrapped it around the back into a three-dimensional potential energy plot. And so the surface here, represented by the circle, is the potential energy of copper iodide and pyrazine separated. This is all qualitative, not quantitative, but I hope that this helps to clarify things for you as much as it did for me. So the depth below that circle shows us the difference in potential energy between the reactants and the product. And so we can see that you can go either to orange or you can go to yellow, and that the orange and yellow can interconvert, but the activation energy is quite high, so it doesn't seem to happen very often. And between yellow and red, we know that this took over a month to happen in the previous experiment, so we can see also that that is a very slow, very energy intensive reaction. But we see that the orange and the red are able to integrate quite easily, and so we know the activation energy must be quite small between those two. So this allowed us to just get a better feel for the relationships. But one thing you do not see is copper iodide and pyrazine spontaneously forming the red compound without first going through the orange intermediate, or the yellow intermediate, if you will. Now, this is important because this orange compound is very hard to crystallize. And so we really wanted to be able to verify this relationship. So that way we could say officially that we were making the orange compound in our research. And so this relationship actually follows what's known as the Oswald step rule, which is an empirical observation. It says that the most stable polymorph is not the one that forms first, but rather the product that is most like the reactants is the one that forms first. And so in this case, the copper iodide and the pyrazine will first fall down into the orange polymorph and then to the red, but never go directly from reactants to red because this orange is in the middle. So this says that if we see orange in our products, we can with relative certainty say that we did in fact make the orange product and not a mixture of yellow and red. So then we wanted to see if acetonitrile would behave the same way in an assisted accelerated aging process. And so when we did this, we found that after 1 hour, we had formed this bright orange compound, this bright orange polymorph, and that it took around a week for this to mostly turn red. But even at 1 week, it was still a mixture of orange and red, which you can't see very well in this picture. But remember that with water, this only took about 30 minutes. And so the length was much longer with the acetonitrile. And we wanted to understand how the solvent can change the reaction mechanism so much. And so that was this was our big question. How does this happen? And so we found a study by Barth et al. That actually looked directly at how copper iodide solvates in acetonitrile. And we found that copper iodide forms these dimer structures that are surrounded by 4 acetonitrile molecules that are coordinately bonded to the copper. Now, this mobile dimer phase, as we call it, seems to be much easier to form this ladder motif in the yellow compound whenever you have these mobile dimers in place. And so they can snap together, and like Legos basically, and form these ladder structures, which can be combined through pyrazine. And so this is one pathway where the solution synthesis in acetonitrile can lead to this yellow compound while completely ignoring the other pathway because there's so much acetonitrile around. So looking at that in a general reaction mechanism, we have crystalline copper iodide here. The acetonitrile diffuses through that crystalline lattice, breaks them into mobile dimers, and then the mobile dimers are assembled when the pyrazine is added into this yellow polymorph. While in the case of the pyrazine diffusion, if the pyrazine diffused through the crystal lattice, then it's going to break up the crystal lattice into these isolated dimers surrounded by pyrazine, which forms the orange compound or the orange polymorph. But then this is kind of unstable because it has these very large pores, it's two-dimensional, and it just generally is not very stable. It's easy to crush those pores. And so it will spontaneously decay into the more thermodynamically stable red polymorph over here. And so what's interesting about this is that it presents us with an interesting conclusion. So in water, the primary mode is going to be this one. The primary path is going to be going to red or orange and then to red, while in acetonitrile solution synthesis, you're going to go through the mobile dimer phase and then to the yellow polymorph. But then if you are in acetonitrile-assisted accelerated aging, then both of these pathways are available. The acetonitrile could solvate the copper iodide, but the pyrazine is in much higher relative concentration to the acetonitrile whenever you're using 45 microliters of acetonitrile. And so the pyrazine pathway is the one that's going to take over, and the orange and then red are going to be shown rather than this yellow pathway. The last thing of interest here is that most copper iodide MOFs have been made up to this point in literature using acetonitrile as the solvent. And so in those solution syntheses, we could be only seeing one kind of special case of copper iodide's chemistry because of this mobile dimer phase that does not occur in solid phase chemistry. Does not occur in accelerated aging. And so this is really, really interesting, and it points to that maybe there are other polymorphs of already studied systems that have just not been seen because they used acetonitrile in the synthesis. So you might be saying this is all very interesting, but as every person who does basic scientific research has to answer, what does it do? Excellent question. First, I just want to point out how pretty these things are. Here are the compounds that we've been discussing over the last 30 minutes. And over here are something I'm going to come back to. But these over here is a non-fluorescent compound. So these are being exposed to UV light and fluorescing visible light in those photoluminescence properties that we discussed earlier. So this is a really important part of how these can be incorporated into lighting and that kind of thing. So potential applications in lighting. But the most exciting part about this work, I think, is the extrapolation of this very, very energy and solvent efficient synthesis method. So specifically, I discussed how there may be other polymorphs that are available in other systems, but that those polymorphs aren't available because we use acetonitrile and we form those mobile dimers. Well, to prove the point, we actually did this same accelerated aging procedure on another system on another copper iodide ligand system, and we were able to make this novel compound in the middle here that has not yet been reported, and we're still awaiting structural characterization on. But this here is the recognized polymorph of this system, and you can see the difference in fluorescent colors between the two. And this is very exciting. We're currently waiting to see what what the structure is and all that kind of stuff. But we'll have a paper on that soon enough. But this shows the possibility of having these other structures be in these systems that we just haven't noticed yet, we haven't seen yet. So, and lastly, this is a base for mixed ligand MOFs. These are very simple, non-functionalized MOFs, and so in the future we may incorporate triphenylphosphine and other kinds of groups in order to enhance the fluorescent capabilities of these compounds. And lastly, by looking at these synthesis pathways and looking at all of this, we've really, I hope, provided insight into how these specific MOFs form, and in general, expanded the understanding of how these MOFs form as a whole, and how we can take advantage of that to make more energy efficient and solvent efficient techniques for making these compounds. So in conclusion, we were able to make this red polymorph of copper iodide and pyrazine that has interesting fluorescent properties, but was not, which did not have an efficient synthesis pathway before the work of Cappuccino et al. But with our work, we've simplified that even greater and presented a lot of interesting mechanistic insights into how this polymorph forms. We were able to plot out these polymorphs by using this three-dimensional potential energy plot, which I don't know if this is going to be, I don't know how well this can be extrapolated. They're kind of difficult to draw, but they really did help us in understanding the relationships between these polymorphs and how we could connect the dots, if you will. And so they were very useful in understanding this system. And then we were able to use those insights from Cappuccino et al., whom I have so much thanks for, great thanks for, to plot out two separate pathways that can be taken when acetonitrile is present and when acetonitrile is in very low concentration or is absent. And this allowed us to understand why the orange polymorph may form over the yellow polymorph and vice versa. And lastly, we did all of this in the hope that we can make these syntheses more environmentally friendly, less solvent intensive, and less energy intensive overall. And to use earth abundant metals, and hopefully in the future use metal oxides in our research in order to expand on this work. Lastly, I just want to thank Dr. Ho for her guidance and patience over the last year. And I want to thank all of you for listening. I look forward to the Q&A section. And here's just a couple of the people who made this work possible. Thank you very much.
Hey, fantastic. That was a great talk and full of interesting stuff. So let's go ahead and we'll just jump straight into the questions. So the first one here is, what is the role of the water in causing the polymorph change?
Right. So we asked this question, at the start. We're like, okay, well, it's not solvating the copper iodide, so what is it doing? So pyrazine, when it comes out of the bottle, is a solid. And so what we believe the water is doing is basically just providing a solvent for the pyrazine and allowing the pyrazine to diffuse into the copper iodide lattice structure. And that's what's causing the orange structure to form.
Okay, so it effectively provides it provides mobility for the pyrazine.
Exactly.
All right. You touched on this a little bit, but I'll ask the question so you can maybe expand on it a little bit further. Do you think that this type of mechanochemical synthesis can be applied to other MOFs as well?
Yeah, absolutely. And, mechanochemical and accelerated aging, I think, is the one that's currently less acknowledged in the literature. Mechanochemical is great, but the one thing about mechanochemistry is that it requires you to have these expensive techniques and in a lot of cases, like have a ball mill, or I know there's other systems as well. But with this accelerated aging process, it seems that you can do these procedures with, just dry grinding the materials and then setting them to the side. And so, yeah, definitely can be expanded to other systems. And in particular, as I stated, we're really excited about using metal oxides in this research, because then we can get away from even using these more dangerous and more expensive and more processed copper or metal halides that are common in the work right now.
Interesting. Do you see any limitations on the accelerated aging synthesis methods?
Oh, certainly. Yeah. So there's definitely, it's not a fix all. Who knows how far it could go? It's got to be, that needs to be determined by future research. But my first instinct with that is with porous structures. This has been noted in mechanochemistry, and I'm sure that it will be the case once we get more into depth with accelerated aging, is that the pore size is quite small with these compounds when they're made through these kind of solid state synthesis methods. In the photocatalytic properties and the fluorescence properties, pore size isn't as important. But whenever you get into catalytic properties, the pore size is very important, and having a consistent pore size is very important. And so it will take a lot of research, I think, to bring accelerated aging to the point where we can control the size of the pores and maybe find ways to expand them as well. So that would be the main limitation to this process.
Okay.
In my mind.
That makes sense. So if you allow the orange or the red polymorphs of the copper iodide pyrazine MOFs to dry out, so not necessarily heating, but like let's say you expose it to air, right? And so like you allowed the water, whatever water was going to naturally come off at room temperature, do they change back to yellow, or are those two polymorphs at least relatively stable enough to do that?
Well, that's a very interesting question. So there's a bit of uncertainty there. So thermodynamically, the red polymorph should be the end all be all of all of these, because it is the lowest in energy. But we did have one very interesting result from an experiment that we really weren't able to replicate. This is completely just like, we didn't quite go too far down this road. But what we found is that over time, some of our samples did end up with a yellow dust on them when they were exposed to air for a long period of time.
Okay.
And so we're unsure we're pretty sure it's not the red compound that's decomposing, but it may be that there's amorphous orange polymorph in there, and that orange polymorph may have some pathway to get to the yellow more easily than we assume. And so there could be something going on there. But the orange and yellow have both been reported to be fairly shelf stable by other studies in this polymorphic system. But the yellow one in particular is interesting because it's high in energy in comparison to the red, but it takes a very long time to decay down into the red. Like you have to leave it in acetonitrile for over a month to get anything. So there's definitely some question on stability. The thermogravimetric analysis only required a temperature of about 100 degrees Celsius to convert the red and orange onto the yellow compound. So thermally, they are kind of unstable, and that's a possibility for like functionalization to perhaps stabilize these compounds.
Yeah, well, I guess that makes sense too, because if the water is what makes it change to the orange and red polymorph, it would make sense that about 100C, you drive the water off maybe, and somehow that causes the rearrangement back to yellow. But that's very interesting.
Actually, I would rephrase that because it's the pyrazine. The yellow polymorph is actually a 2-to-1 polymorph. I got this straight. So it's a 2-to-1 polymorph.
Okay.
So what seems to happen is the pyrazine is actually being driven off because it's a volatile organic.
Gotcha.
So the water is not actually terribly important in stabilizing them. It is important in the reaction happening. So if you take for example, if the solvent leaks out during the accelerated aging process, it'll just get frozen in whatever state it's in. And then, maybe decompose to yellow if it gets heated during that time.
Yeah.
Yeah.
Interesting. Okay. All right. That's very interesting then.
Yeah.
It's a really interesting chemical system. That's very cool.
Yeah, I really liked working in this as a polymorphic state. It's like there's just so many interrelations you have to keep track of, and like
yeah, that's exactly it. On the surface, it seems like a straightforward thing, but there's clearly a lot going on that you have to account for. So that makes for some really good science. So
absolutely,
very cool. Well, that looks like that's all the questions we have. So I will say thank you again for coming out and presenting your work. For a year's worth of work, this is really impressive. You did some really cool stuff here. So thank you for agreeing to present and doing a great job with the actual presentation itself.
Thank you so much, Ben. I appreciate your time, and thank you all for listening.
Yeah.